This SMS is basically to code interrupt service routines to effectively to use MCU timers. Now let's go ahead and read all these and see what happens. Coding and interrupt service routines for input capture. From assignment 5, we have seen that delay can be introduced by having the CPU perform meaningless operations for a specific amount of time. So assignment 5 is basically we did delays like using various you can watch my video on delays like in that one we had to, if we have to achieve 1 million delays, what we had to do to make it achieve, and there are various methods we can use to achieve that. Okay, that's basically it about it, but here we are gonna see more details. These delays are no way accurate as the CPU may be forced to handle an interrupt unexpected situation at some point. An interrupt is normally generated by a source outside of the CPU, which in the case of an MCU can be an external circuit as well as the internal MCU systems, timers, communication system, etc. Interrupts generated internally in the CPU are generally referred to as exceptions. We will study these in larger assignments, later assignments. The CPU processes interrupt signals by running user-specific code to handle them. It does this by first completing the current instruction that is in progress. Then it saves the state of the CPU, PC register values on the stack, and it jumps to the interrupt handler, which is often referred to as the interrupt service routine (ISR). The interrupt ISR performs whatever the operations are needed to service the interrupt, and once complete, a special instruction is run which restores the save register and PC, which was stored in the stack earlier, allowing the CPU to return to the running process prior to the interrupt signal. The timer for an ISR to start and finish can vary, so we can rely on instruction delays alone for generating accurate timing events, as many things happening inside and outside the CPU can affect its overall cycle count. To solve this accurate timing problem, the MCU includes special timing hardware which results in an acceptable level of timing precision. The whole timing system is derived from the free running timer FRT. The FRT is an internal clock in the MCU which operates similar to a wristwatch. We can set alarms or record the times in which other events occur. For example, let's consider a 24-hour clock as it is linear throughout the day. A day begins at 0000, and as every second of time passes, the clock increases by 1 second, the seconds from 0 to 59, at which points the second overflow it goes back to 0, and then minutes increase again from 0 to 59, where just like the seconds, an overflow occurs, resetting the minutes back to 0 while increasing the hours, in this case from 0 to 23. After that, the clock wraps back to 00000, yet another overflow. This particular overflow signifies that a new day has begun, and in some cases this isn't all that important, as humans generally schedule themselves daily. For example, if someone wakes up at the same time every day, goes to sleep at the same time as well, as knowing the actual day isn't all that important. The FRT is an analogy of this. It begins at 0 when the MCU is powered on and increments every e-clock cycle, and it resets back to 0 after it reaches 65,535 or FFF hexadecimal. It is a 16-bit value. The MCU e-clock is 2 MHz. This overflow will happen about 30.5 times per second. If that amount of time is not preferable for our application, we can change the e-clock to a faster or slower clock, or we may not even be concerned when it overflows back to 0, just like someone with a regular sleeping schedule. But in case we are there should be an efficient way of knowing when it happens, falling or always examining a value constantly, looking to see if a condition is met. We cannot only be a burden on the CPU, but there is a good chance we could miss the switching of the condition question if we are busy doing something else, such as examining some other information or performing an ISR A good way for humans to know when a new day begins is to set the alarm for 00000 as opposed to constantly looking at the time on the clock. The designer of the MCU used the same strategy to avoid polling their solution. Polling Their solution was to have special hardware to do checking, but then tell us if we want by using interrupts. When the hardware detects an overflow on the FRT, we can choose to generate an interrupt, thereby allowing the CPU to run an ISR so that we can know when this happens and then do something about it. In general, we enable interrupts by setting interrupt mask bits to 1. In our MCU register, using 0 turns them off. When a mask is set and an interrupt occurs, the CPU will pause the current program, serve the CPU state, and then go and run the intended ISR. There are a number of hardware devices inside MCU connected to CPU, each which has a fixed vector or pointer which instructs the CPU where to go when a particular interrupt happens. These vectors are at the top of the memory near the reset vector. In some cases, there can be many possible sub-events associated with each interrupt. To solve this, the MCU designers allow us to see result of the hardware checks. These are called interrupt flags. The set of bits which are individually set to 1 to indicate which interrupt occurs as well as a particular sub-events. It is good practice to inspect interrupt flag during ISR to ensure we are processing the correct event. Depending on the task needed to be performed in an ISR, there is also possibility that another interrupt from the same source could occur before we are done running the current ISR, which could lead to cascading or nested interrupts. This can be very bad, especially if we are not expecting it. To solve this, the MCU designers made it so we can control whether or not we want to another interrupt to occur while we are in an ISR. When we enter an ISR, the ICCR flag is automatically set to 1, indicating we don't want nested interrupts. To allow them, we only need to clear ICCR flag with CLI instructions. Once we are done processing an interrupt, we need to tell the hardware which generated it that we are finished. We do this by clearing the corresponding interrupt flag prior to leaving the ISR. It is done by writing a 1 to the same register and a bit position of the flag we inspected initially. This ensures that the CPU will not return an ISR after it is completed. This may sound counterintuitive to clear a bit by writing a 1 to it, but interrupt flags in the MCU are not normal memory. They are special circuit in which the behavior is different based on whether or not the action is read or write when accessed. When reading, we see the status of the flags, while writing, we indicate which values to set to 0. This is preferred as there may be other bits set in the flag which were generated by other interrupts. It avoids the problem inadvertently clearing other interrupt flags. The FRT overflow is just one many timing interrupts. However, we will use it in part C. For this part, we will first explore the interrupt capture system. This is a feature of the MCU which can monitor hardware line and determine the exact time in which an external source switches it from 0 to 1, 1 to 0, or both. The time in this case is value of FRT 16-bit. Can therefore use this feature to determine whether a signal change occurred and set up a new event based on the initial change. An ISR can be executed soon after signal change, but we know there can be delays from when the signal changes to when the code is actually executed. The MCU helps us by saving the FRT from its register TCNT into another register TIACX, where X can be between 1 and 4. At the precise moment the signal change is detected, so we can use it in our ISR when it's eventually executed. To demonstrate this in cortex-m, we will set up a virtual switch which will use to connect to one of the input capture lines. PA0 IC is only available on a certain pins of port A. You can do this by going to connect switch menu and select pin PA0 IC3. So let's go ahead and do that. So this is the A part of the assignment I'm dealing with, and in order to do this, first I'm going to the following this one, connect, and then switch, and then pin PA0 IC3. That's what mentioned to be connected. Okay, and then press connect, press the connect. Okay, where's that? Yeah, here, connect, and then press OK to close the window. Okay, that's the only thing has to be done. And once I close the window, I'm getting this. Okay, this is a switch and it's currently off. A new window will should appear. You may have to make it larger to see the title, which shows the state of the switch, as well as move it around. Left clicking on the switch toggles value. We can alternately determine the state of the switch by reading PA0 or bit 0 of port A. But as details of the polling is never a good way to do this. The IC can let us know when we can read the switch, or we could just set up specific conditions, generate the IC on the rising falling edge of the input. Open this file in the cortex-m, so I already opened that. You will notice a lot of EQs at the top of the file. This is to instruct assembler on the location many MCU registers. The first two are default value, which will be used setup system. See the code beginning start label MIC3 ICL2. Okay, he's mentioning this one, MIC3 and ICL2. These two are here, and need to set properly as they will be loaded onto TMSK1, TCL21 respectively when code starts. Okay, these two are, you need to, okay, so this is in the reference manual. As you may see, this is mask bit for IC3 CTMSK1, IC3 TCATL21, and these are the reference manual. If I go here, TMSK1, okay, these are registers in the, these are kind of registers. TCTL2, TL2. Okay, so from this one, you know, like there are various things, like I'm getting a 16 matches. So you have to go around and find what values to set for them. Actually, code start, you will need to look at the reference manual to discover which bits needs to be set. We need to configure IC3 behavior with ICL2 so that it capture any edge. H3B, H3A approximately interrupt mask for IC3 must be set to 1. IC3I must be set to 1 for MIC3. Okay, and any ISRs should do what they need to do as quickly as possible, as there could be another interrupt coming up very soon. In this case, we will use the IC3 ICR to record the time switch was changed. We can do this by saving the 16-bit value at TIC3 into a reserved space in RAM called iTime. We will also save the state of the switch by reading PA0 port A bit 0. and storing it in I state, we should turn off the other bits 7 to 1 before serving it, as any of those could be on, as they correspond to other signals on code A. Since a lot of interrupts can happen on an MCU, we need a flag that tells us these new values we saved are valid. We do this by setting I flag to a non-zero value. 0 means invalid or empty. This programming technique of saving information and setting a flag is known as a mailbox. We will discuss it shortly. With ISRs, we must also remember to clear the interrupt flag by writing 1 to the correct bit position, same position as TMSK1 in T flag 1 before we leave. Otherwise, ISR will just run again. Once that is done, we can then leave the ISR by assuming RTI instructions. Essentially, the ISR will put information into mailbox iTime and iState and will set a flag on to tell us there's something new in there. It is called a mailbox. As a direct analogy, mailboxes placed at the end of the driveway near the street. The flag on the mailbox is raised by mail person after delivering the message to let you know there is a new message there, so you don't have to go look inside to know there's something new. We are putting information into our mailbox, as processing it in the ISR would be too time consuming. Instead, we process it in our main loop, the part of the code that repeats over and over again, waiting for something important to happen, does something about it, but it can take as long as necessary to do it. This loop isn't time sensitive. If we examine the main loop, we can see it first waits for an interrupt to happen. As we know, the WAI instruction prepares the system to handle an interrupt quicker by serving the CPU state before an event to increase response time. When the interrupt does happen, the ISR will run. When ISR leaves, the code WAI will continue. The next check for the mailbox set I flag. If it isn't 0, then we know something is waiting there for us. We next print the value of the FRT as well as the value of iTime. The value of the FRT when the switch was toggled, followed by a space, and then the value of iState, which is the new position of the switch. Here we will be able to see how long it takes from when the switch is thrown to when we can actually process the result. It isn't immediate. The FRT TCNT must be read using a 16-bit read, LDD, LDX, or LDY. These three are 16 bits operations. And then not just because it is a 16-bit word, but rather it avoids the potential for overflow that may happen when you issuing two separate 8-bit reads, as the FRT may change significantly between those separate reads. Before finishing up, we make sure clear the I flag, so if on subsequent interrupts potentially from other sources, we don't repeat this process of displaying the mailbox in contents if new information isn't present in it. We then continue processing additional mailboxes which we don't have yet but will in part B, and then go back, wait for another interrupt. The time send information serially to the PC terminal requires a lot of time, so doing this inside an ISR may result in other interrupts being delayed, which could cause timing problems. Overall, it is good practice to always use ISR mailboxes and main loops to process information. This is the whole basis of how the graphical user interface on your phone and the home PCs operate. Your task is to write core part of IC3 ISR, follow commands to add code after the IC3 vect label. The code for the ISR should be less than 15 instructions, as it should run quickly. When you run your code, the serial terminal should already be set to 120,000 baud. output should show the current FRT, the FRT value when you press the switch, followed by the state of the switch, 1 for on, 0 for off. The difference between those two FRT values should be 65 decimal, indicating that it took 65 cycles from when the switch pressed until we could begin processing the action. If the system had a 2 MHz E clock, this translates to 32.5 microseconds, which may or may not be long time depending on the application. Note that FRT values shown will eventually overflow back to 0 every 65,536 cycles. This can happen quickly in real world system, but we will fix this later in part C. Okay, so these all are the things like explanation of what's happening. Let's go to the code and try to complete it. Okay, now initially we have this, turn switch on and off, and then we have to also have this view serial receiver open, and this one has to be set to 125,000 baud. I already have that one, so nothing to change here. And currently let's run this one and see if something happened. Currently I didn't change anything here. They also mentioned I had to change this one using the reference manual, and also I had to adjust the code here to make this one work as it expected. Okay, and others are already there. Okay, so let's run this one without doing anything and see what happens. Okay, currently I have the switch on and off. I'm turning on and off, nothing appearing, nothing happening, so nothing works currently right now. And then I looked at the reference manual. I found out the value that has to be set for this one is 1, and this one is 1 1. Okay, now let's reset. Let's try running this and see if it's happened. Something happening, but nothing here. Like when I turn on and off, nothing happening. So I'm not gonna worry about this for now. Let's complete this part of this. So here what they're asking us to do is okay, add your ISR code here, IC3 vector introduce. So here's where we have to write the code, and the mentioned instructions are check proper interrupt flag to make sure we should be here, read flag T flag 1, and then it mask it and it by mask bit. If Z flag is set, get out by going to IC3 end. IC3 end is here. Return from interrupt RTI. And if so, clear the interrupt flag. Write a 1 to mask bit T flag 1. Set T flag set flag on input mailbox to say something is there. Write to I flag. Record when it happened in the item variable. Copy from TIC3 to item. Copy the state of the switch to copy from port A bit 0 ending appropriately and store it in. Let's do it. Okay, so first we have to read T flag 1. It is basically loading the T flag 1. So to load the T flag 1, we can use the LDA, load to accumulator A. And T flag FLG1. Let's write the comments as well. Here what we are doing is read that value of T flag 1. Okay, and the second one is saying and also like and it by mask bit, and we had to do the AND by mask bit. Okay. Mask bit is this one, and that is in binary. Percentage mean binary. So I have to do that here. That is 8-bit value 1 0 0 0 0. Okay. Yeah, what you are doing? The double tap for the double tap. Okay. Mask the result. To isolate the IC3 interrupt flag. Then if C flag is set, get out by going to IC3 end. So the C flag will be set if branch let's see, BEQ. Yeah, branch if equal to 0, we can do that. IC3 end. Here if C flag is set, get out by going to IC3 end. Okay, and then if so, clear the interrupt flag. The way to clear the interrupt flag is by storing. When we store, it's going to clear. So STAA C flag 1. Clear the IC3 interrupt. IC3 interrupt flag by writing 1 to it. Okay, set flag on input mailbox to say something is there. Write to I flag. Okay, for this one also we store it. I flag. We have set the flag to indicate new data in the input mailbox. And then record when it happened in the iTime variable from TIC3 to iTime. Copy the state of switch 2, copy from port A bit 0, ANDing appropriately and store it in I. Okay, so let's do this one first. So record when it happened in the item variable, copy from TCI3 to iTime. LDD TCI3, not TIC3. Copy the value. This one, what does it does in it? Copy the value of TIC3, time of the event, to the iTime variable, and record when it happened in the item variable, store it as well. STA STD, because we are loading with the accumulator D time. Store the value in the register pair D in the, so we can say already store the value in the ACCD D into the variable item. Okay, that is this. Lastly, copy the state of switch 2, copy from port A bit 0 by ANDing appropriately and store it in I state. Okay, so load from port A, LDAA, port A, and read the state of port A. This one does read the state of port A. AND operation, for the AND operation we just use the mask bit, that is 1, put it in a binary, 8 bits, 1. Mask the result, and the result to isolate the state of the switch bit 0. Okay, and then STA, store it in I state. Store the state of the switch in the I state variable. Okay, and that's basically it. Then okay, so this is what has to happen, and that's the instruction, and there's nothing else has to be edited or done. So let's go ahead and run this one and see if it works properly. We are getting any error, or currently I'm not seeing any error. I'm just going to try turning on and off. So it's coming 1 0 1 0. That's what has to happen. Okay, so it means our program is running successfully. And that's it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.